Catherine Matias from Paris. Catherine's worked widely in sort of statistical aspects of biological networks, and has also worked on latent structure and hidden Markov models, and she's going to be talking about statistical clustering of temporal networks through a dynamic stochastic plot model.
Okay, thank you, and thanks to everybody for being here for the last talk of the day. And also I would like to thank Sophia and Patrick for this wonderful workshop and also the wonderful program, because it has been great for the whole 6 months, so thank you. So I'm going to present a joint work with my colleague Vincent Miel from the University of Lyon 1 in France. And so it's about a dynamic stochastic block model to cluster temporal networks. I'll explain that. So first I'll spend some time about introduction and the motivation of this work that comes mainly from the study of contact networks in ecology. So my colleague is in a biology lab, and he was interested in animal contact networks. So animal contact networks are used by ecologists in order to study the animal sociability, and there have been a lot of papers about that in the last few years. And first I will talk about static animal contact networks. So these are built from different type of data. This can be field observations of associations between animals. This can also be trapping data. So you have a system of different traps, and once you have two different animals that are trapped at the same location, then you consider that they have been at the same place around the same time. So you consider that there's an association between those animals. But these are not the most common type of data that you can encounter. Nowadays we are having a lot of sensor-based measurements. So the idea is that you put a chip on the animal and you can have GPS location of that animal. And so the proximity of the animals is recorded, and when they are at some certain distance, you record an association between those animals. So in the static context, the idea is that you have n individuals that will form the nodes or the vertices of your graph, and what you observe is either presence or absence of a contact, or most often you observe a frequency of the contact between those two individuals. So these will form the edges of your network. And now we are going from static to dynamic data in order to try to study the dynamics of animal social structures. So the dynamic contact networks I'm looking at, these are not exactly temporal networks. I put temporal networks in the title, but in fact what people call very often temporal networks is more like a continuum of observations. Here we will be interested in snapshots of contact networks at different time steps. So typically the time step is chosen by the ecologist. It can be the day, it can be week, months, it can be seasons. So days and seasons are relevant for animals. Other type of time frame, it depends on what you want to show, okay? Depend on the experiment. And in this dynamic contact network, what is important is that the individuals can be present or absent at each time step. So in most of the data set that you encounter, you need to take into account the fact that some individual will maybe die or lose their chip during the experiment, and you don't want to throw this data away, because otherwise you will have a loss of information that is important. And also when you are studying animals at the season level, then you have some animals that are born during the different events that you consider. So it's important to take that into account. And so the formal definition of these contact networks is that you have T different time steps, capital T different time steps, and at each time step you have a number NT of individuals that are present, and the total number of individuals N is much less than the sum of NT. So that means that a lot of individuals should be present all along the data set, otherwise you don't see any signal, so you cannot do what's going on after if you don't have a lot of individuals present for all the time points. And here again, you record either binary information about presence or absence of a contact, or weighted information. Most often it will be a frequency of contact, but it can be anything else. Okay? So why do we want to study these dynamic animal contact networks? There are many reasons for that. One of the reasons is to ask the question, is there a social structure in this network? And so we want to understand if there's a peculiar non-random mixing of your individuals that is a sign for a social organization. So from the ecologist point of view, that's really interesting. And if there is a social structure in this dynamic setup, you want to see if what's the dynamics of this social structure, okay? So there are other questions like how does this dynamic vary with other factors? For instance, this can be the breeding season, the seasonal changes, a response to a stress, the arrival or the departure of a specific animal that has a really huge impact onto the whole group. So these are the questions that can be interesting. And also you can, we've seen a lot of talks about that in this workshop. How can you predict how infectious disease will spread among this network? Here I will only focus on the first two questions. Is there a social structure and what's its dynamics? And in the ecology literature, there has been a lot of descriptive statistics to try to answer those questions, so very basic statistics. And here we wanted to go beyond these descriptive statistics and propose a statistical model for studying the organization of these networks. So that's all for the introduction. Let's go into the details. How are we going to model those networks? So first I want to explain the problem. If I have a network, let's say that one, that I observed at time t1, what I want to do is cluster the network. So for instance, finding those labels, which are the colors on the nodes. Okay? If I have another network, so here the set of individuals is roughly the same. So I've encoded the positions. Here individual number 6 is the same as here individual number 6. So at time t1 you observe a set of relations and you cluster the graph according to your favorite method. And at time t2 you observe another set of relations between the same individuals, and if you use again your favorite clustering method, you will end up with, let's say, that clusters. Okay, so now the question is how will you interpret these clusters? And okay, let me go back for a minute. So for instance, with this cluster, I will say, okay, nodes number 1 and 2, they were in the yellow group at this time point, and they change to the blue group. And this node number 3, he stayed in the same yellow group from the 2 time points. Yeah?
Do the node labels come from a scientist typically, or from an actual sort of clustering procedure?
Do what come from
the node labels, the colors here, do they typically come from?
So that's your clustering procedure. So for instance, you use a spectral algorithm or a modularity-based approach, you cluster the nodes.
They're not given to you by...
No. I'm just trying to explain here what's the problem when you want to cluster graphs in a dynamic setup. Okay?
But the colors are not important, right? They don't represent...
Yeah, I'm going to that point exactly. So if I choose those colors, I can have an interpretation of this clustering and say that, okay, these nodes here, they change group from time t1 and time t2. But of course, the colors are not important. So what does that mean? I can take any permutation on the colors and change the colors according to that permutation, and that's the same clustering. So if I do that on the graph on the right, for instance, and I change blue and yellow color, I will have a completely different interpretation of the dynamics of the structure. Okay? And so that's the problem here I want to tackle. I want to deal with the label switching across time. So if I cluster separately the two graphs, this is defined only up to a permutation on the colors. And so I cannot interpret the change of group along the different time points. So what I want to do is give a method that will cluster this in just one shot and in a way that I can interpret the change of groups or the fact that the node will stay in the same group from one time point to the other time point. That's my goal. Is that clear? Yeah? So I want to see the evolution of the individual nodes. I want to be able to claim that one node is changing group between two time points and that the other node is not changing group. So we want to obtain a smooth recovery of the cluster across time. So how are we going to do that? Just a set of formal definitions. So what I will observe is a set of adjacency matrices. So y1 to y capital T, these are my graph snapshots. And each yt may contain either binary, discrete, or even continuous values, whatever you want. You just put then a parametric distribution on these values and you can deal with whatever you want. An important thing is that these adjacency matrices here, they deal with individuals that are present at time t. Okay, so this set of individuals can change from one time to another time, but I have a whole set of individuals that is stable, and I consider the largest set of individuals. So why do I want to do node clustering? Node clustering is interesting because it models the heterogeneity in the nodes interactions. This can help me summarize information about my networks. And to do node clustering, there are of course many different approaches. Among them, one can cite spectral algorithm, community detection, and model-based clustering. So I'm a statistician, I will do model-based clustering. Yeah?
I have a question about the number of clusters.
Yeah?
Are they required to be fixed from a time to a time? Or?
That's really too early to answer. So I will show at the end that yes, I will fix the number of clusters to be constant across time because I believe, I'm not sure we have enough information to estimate the different number of clusters per time. So I have a global criteria to select for the number of clusters when it's fixed. But I'll come back to that later. So among the many model-based clustering methods, I've chosen the stochastic block model. But okay, it's a choice. And in the following, I describe the case of undirected graph with no self-loop, but that's not important. We've implemented the method with directed graphs and also self-loops because we are looking currently at food web networks where the nodes are species, and so you can have species, not individuals, but species that eat the same other individuals from the same species. So you can account for self-loops, it's not a problem. Okay, so the stochastic block model, we didn't have many talks about it, but I presume that most of you know what it is. In the binary case, it's just the following. So I have a graph, I don't have the colors, I want to put the colors on the nodes. So how do I do that? The colors are the groups. I assume that there are two different groups. The groups are encoded through these latent random variables. So ZIT is the group of node I at time t. Okay, and what you observe is either presence-absence. In the binary case, it's presence-absence of an edge at time t. So that's given through the adjacency matrix YT. And you assume that conditional on the latent groups, those random variables are independent, and here they are just Bernoulli distributed with a parameter that depends on the time and on the group of the two nodes at that time. Okay, so that's really simple. And you can generalize the stochastic block model to the weighted case very simply. So in the weighted case, what you observe is either zero values, meaning that there are no connection between the two individuals, or anything, let's say a weight if you want, but this could be any vector, random vector. And you put a parametric distribution on the distribution of the y's conditional on the z's. And so to account for possible sparsity in the network, so when I mean sparsity, I mean there are some edges that are not present. I don't want a full, completely full adjacency matrix. I design this conditional distribution as a mixture between a Dirac mass at 0 and any parametric distribution. So for instance, this could be Poisson, this could be Laplace, this could be Gaussian, whatever you want. Okay? So you mix that with a true 0 if you want to, in order not to have too many edges in the network. And so here, beta is what I call the sparsity parameter. Again, it's not the sparsity in the same sense as Mariana. It's not the same sparsity as the one that is studied in graphon, etc. Okay, but I call it a sparsity parameter, and gamma is the parameter of the distribution of the weights. Okay, so that was for the static part of the model. I just put a stochastic block model, and now I want to do it dynamically. So the simplest thing to do is just to put a Markov chain on the latent random variables. So I will assume that across individuals, the groups Zi are IID, and across time, each Zi is in fact a stationary Markov chain. So I've put stationary Markov chain, but I don't need the stationary. It's completely useless. So you can forget about that. So this Markov chain has a transition matrix, which I call pi, and some initial distribution alpha. So here it's a schematic representation of the model. And you can see that it's something like a hidden Markov model. So you have this latent set of random variables that evaluate as a Markov process, and conditional on the latent variables, you have those observations which are just the adjacency matrix at each time step. And so the specificity is that here I assume that every row here in the latent process evolves independently of each other. So each node evolves independently of each other. And so my goal here is to infer the parameter. So the parameter is the transition matrix, and the parameter, so the sparsity parameter and the parametric component of the distribution of the weights, the edges and weights, conditional on the latent groups. And so I want to infer those parameters and recover the clusters so as to follow their evolution through time. Yeah?
You don't infer alpha.
Oh, so I dropped the alpha because I suppose it's the initial stationary distribution, so it's a function of the pi. And otherwise, if it's not the stationary distribution, I don't know how to estimate it, so I drop it anyway. In all the cases, I drop it.
Do you know what Q is?
I will give you criteria to estimate it at the end. But as Lamia said, Q is constant. Okay, that's the same. I don't have a QT per time point because I believe it wouldn't work. You could do it, but I believe it wouldn't work with data sets. Okay, so obviously we're not the first one to do very similar things. Here I just mentioned two works that are very close to ours, and I'll try to explain the differences. So there are two papers that are very close in the sense that they use a Markov model for the latent group membership, and the stochastic block model as the static part of the model. So that's the paper by Yang and co-authors, and Xu and Hiro here. So both those papers are in the binary setup also, and we do the binary and the weighted setup. So main differences. Here we allow for both groups and parameters to vary with time. So in the paper by Young, only the groups could vary with time and not the parameters. And in the paper by Xu and Hiro, both could vary. If you let them both vary, I will explain in the next slide that you have a huge identifiability problem. So you need to add at least a small constraint in order to be able to recover everything in a rigorous way. So I will discuss valid assumptions for the parameters identifiability. Second, as I already said, we model binary as well as weighted graphs. Third, we propose a model selection criterion for the number of clusters, so the number of groups Q, and they didn't. And fourth, I will discuss in the simulation a proper clustering index for measuring the classification performances that takes into account this label switching across time. So I'll go back to this at the end of the talk. So let me explain the identifiability problem with a toy example. It's really very easy to see that if both the parameters and the group membership can vary with time, then you cannot recover the parameters. And let me explain that to you with a toy example with 3 groups. So here there's the red group that is a hub, let's say, and we will have 2 other groups, a community and a periphery group. So these are some type of groups, okay? I have this graph that I observe at time t1 and a second graph observed at time t2. And in the first scenario, so assume that you have recovered this clustering of the nodes. In the first scenario, you will say, okay, from that time point to that time point, I had the set of nodes from 2 to labeled from 2 to 6, here the yellow nodes that form the community, and at the second time point they are what I call peripheral nodes, okay? And in the first time point, this set of nodes here in green, they were forming a periphery, and at the second time point they rather form a community. And here the parameter values didn't change from T1 to T2, meaning that yellow is always a community and green is always a periphery. Okay? In the second scenario, I will change, so from that slide to that slide, what has changed is the color here. I have exchanged yellow and green. Okay? So in that scenario, which is the same clustering from a local point of view, I would say that now the group membership stay fixed, but the green group at time t1 was a periphery, and at time t2 it became a community, and the yellow group was a community and it became a periphery. So I have 2 different interpretations. So if I let the group membership and the parameters vary, I cannot recover uniquely. There's not one unique scenario to describe what I can obtain. So thus we had to include some assumptions in order to make the model identifiable, and what we choose to do is assume that there's something that is fixed in the connectivity parameter, and here we choose to fix the diagonal values. So for all the values q, whenever I look at 2 different time points, the values beta QQ and gamma QQ, they do not change from one time point to another. So the other values, beta QL, with Q different from L, they can change. So in your connectivity matrix, what happens is that, so you have here the connections between group Q and L. One sort of minimal assumption we came with is that in every row you need to fix at least something that will not change throughout all the time points, and that will characterize that group. Okay? So we decided to fix the diagonal, but you could fix the first column, saying that one group has, well, say you could fix anything. At least for each row, one parameter should be fixed through time in every row.
It is not QQ prime, it is beta T prime QQ.
Yeah, that's
comma.
a comma. That's
Okay.
a comma that is obviously misplaced. Thank you for noticing that, Mariana. So that's beta
I figured
QQ,
out that it was
comma, second line. That's crazy.
I figured out it was comma and the period.
Yeah.
I saw the period. in
Indeed,
the
thank
second
you.
line.
Thank you. So under this assumption plus some other classical assumptions that are needed, are not needed, but are sufficient to establish identifiability of the stochastic block model, we can prove identifiability up to what I call a global label switching, meaning that the parameters are defined up to a permutation, but the permutation should be the same on all the time points. You cannot choose one permutation per time point, okay? You have to have the same permutation. That's the only way to follow the groups. And we also underlie in the paper that if you consider the affiliation case, so what is the affiliation case? Is when in this matrix you only have two different values, a value on the diagonal and a value outside the diagonal, so meaning the inside the groups it's one behavior and outside the groups it's another behavior. In this case, currently no method, there is no constraint, we didn't find one and nobody find one to my knowledge, that can avoid the label switching between the different time steps. So meaning that if you're using an affiliation model, you cannot be sure that you follow the group along the different time steps. And I will show that in the simulations if I have time. So how do we do inference for this model? We rely on the likelihood, but the likelihood is intractable, as Mariana said, and so that's an awful formula that you shouldn't look at just to explain the likelihood, but it's not important. The thing here, so that's not the likelihood, that's the complete data likelihood when I put the z's which are latent. And of course I cannot compute the likelihood because I would have to sum over all the possible clusterings, and that's intractable. So what we do normally is to rely on EM algorithm, and here with the stochastic block model we cannot rely on EM algorithm because the distribution of the latent variable z's given the observations y is intricate. It's not a product distribution, and so you cannot compute it. So what people usually do in that setup with the stochastic block model is that they rely on a variational approximation. So the idea is very simple. This distribution of the z's given the y's is not factorized. So you take your favorite factorized distribution, you take one factorized distribution and you use it as a proxy for the truth. And here, so my variational approximation will be based on a factorized distribution along the nodes, the different nodes. And for each node, I have a Markov chain because that's the natural way my data is organized. In fact, there's a Markov chain over time. So I use this variational probability as a proxy to the true one, and what I compute in practice with the variational EM algorithm is that criteria J, which is the expectation under this variational approximation of the complete data log likelihood plus an entropy term for this variational approximation. And in fact, with some very simple computations, you can see that this criteria here, J, is a lower bound to the data likelihood, and the difference between J and the data likelihood is a Kullback-Leibler divergence between the variational probability Q tau and the true distribution you want to deal with of the latent given the observations. So if I were able to take Q tau being equal to this latent random variable, to this latent, to this conditional distribution, then this Kullback-Leibler divergence would just cancel, and my criterion J would be equal to the likelihood of the observation. But I'm not able to do that, so I have a loss, and so I'm not optimizing the likelihood of the observation. Nevertheless, we know that in the case of the stochastic block model, the variational approximation does a good job. There are many results that explain that in an asymptotic setting. So, but I will not enter into those details here. And so the VEM algorithm is very simple. That's an iterative algorithm. You need to start from an initial point, and that initial point should not be completely random. It's really critical to choose a good initial point. And then you alternate two steps. In the VE step, you take the approximation here, Q2, that is the best approximation in the family of the product distribution to this distribution that you don't know. And in the M step, you fix this Q2, and then you optimize with respect to theta, the parameter. Yeah?
You use a mean field approximation?
Yeah, that's exactly a mean field approximation, indeed. I should have said that, sorry. So variational EM is exactly mean field approximation. So you can find more details in the paper. And okay, we have a criterion to select for the number of groups. So here we derived, so that's classical with SBM. We didn't invent anything. With SBM and the variational approximation, you use an ICL criterion. This is the value of the complete data log likelihood that you've obtained at the end of your algorithm, and you penalize it. So there are two different penalty terms. The first penalty term is for the distribution of the Z's. So these accounts for the transitions of the Z's. And this is penalized by capital N times capital T observations. And you have a different term for the penalization of the parameters beta and gamma. And this relies on another number of random variables. In fact, here the penalization is dependent on the number of possible edges in your graph. So I don't give an expression here because it depends on the form of the parametric distribution that you choose. Okay, so if you choose Poisson, it will be some form, but it's mainly number of parameters divided by 2 times log the number of possible edges across all the time points. Okay, let me show you a few simulations and a very short analysis of a real data set. First, the simulations. So what I wanted to emphasize here is that we want to measure the clustering performance, and you can see it in two different ways. So the adjusted run index is a way of measuring the quality of a clustering, okay? So a natural way here of measuring the quality of your clusters is to look at a global adjusted run index on the whole classification. So you have a classification for all the different time points, and you look at that quantity up to a global permutation. So the permutation on the labels is the same for all the time points. And what Xu and Hiro did in their paper, they looked at an averaged value of the adjusted run index. So meaning that they computed IRI for every value of t, and they averaged that over the different value of t. So in this sense, you can have one specific permutation per time point, and you're not dealing with label switching between different time steps. So you won't correct for label switching between different time steps with this criterion. And so we have a very simple simulation setups where we look at binary graphs, 100 nodes, two different values of t, 5 or 10, 100 data sets. two latent groups and different transitions matrices for the latent groups. So from low to high, you have low stability. Here the groups change a lot, and here the groups don't change a lot from one time to the next one. And the connectivity parameter, we also have different scenario from easiness going from low minus to medium plus. So in this case, the parameters are very much alike, so it's really difficult to find the groups. And here they are more different, so it should be easier. And we also considered medium difficulty, but in the affiliation setup, so beta 11 is equal to beta 22. I will show you the results. So here you can see box plots about the clustering performances. So in yellow you can see the global adjusted rand index. So the first row is for t equals 5, second row for t equals 10. That's pretty much similar. You can focus on the first row. And from left to right, the scenario increases in difficulty, in easiness. Okay, so left is really difficult. So here, for instance, we can see that with low group stability and low differentiation between the parameters, we do a very poor job. We cannot recover the clusters. But from the left to the right, we do a better job, and when we are on top one, we do a perfect reconstruction of the clusters. And so in this setup, what is interesting is what happened in that third column that shows the case of medium difficulty with affiliation. In yellow, you see the global adjusted rand index, and in gray here, you see averaged value. So you can see that if I look at average value of the IRI, I think that I do a great job in reconstructing the groups. But in fact, if I look globally, I do a really poor job. So I'm not able to correct for the label switching between two different time points. Okay, we compared our method with the one by Young and co-authors, and we used their codes from scratch. And in fact, that gave very, very, very poor results. So these are not these ones. So at the beginning, we used the code like that, and we had less than 0.2 for all the IRIs. So we decided, so in fact, looking into the code, we saw that they were using completely random initialization. And completely random initialization doesn't work at all. So to compare the methods, we decided to run their method with our initialization strategy, and the results are a bit better, but they are still not as good as ours, of course. It's set up for that. Okay. I'll skip that thing and briefly talk about a real data set. Believe me, the simulations are okay because, of course, we've done it so that they are okay. What can we obtain on a real data set? So this data set is the same that Pierre talked about. It was yesterday or 2 days ago, I don't remember. The sociopattern data set, where you have face-to-face encounters between high school students. So here the students were equipped with wearable sensors, and each time they were facing each other, you recorded an association. There are four different days of measurements and 27 students. By looking at the distribution of so we recorded the frequency of interactions. By looking at the distribution of the frequency of interactions, we decided to discretize those frequency into 3 different categories, from low, medium, and high. Okay, so this is a choice that we made. And in this setup, we ran the ICL criterion, and it gives nothing. Okay, so we decided to select Q equal 4 groups just using elbow method. You look at the log likelihood and you decide, it seems to be there. And what can you obtain? So these are the reconstructed dynamics. You don't see much, but okay, you see a little bit, no? So here, that's the first day, second day, third day and fourth day. And you can see each day is organized into 4 different groups. And you can see the flow of the students from one group to the other. So for instance here, between here and here, we have a number of the members from group number 4 that go into group number 2 and some that go to group number 1. So you can see, for instance, that group number 1 and group number 4 never exchange students between the different time steps. So in the paper we have a whole story about interpretation about that. We also looked at the genders of the individuals, and that match our story. Okay, I won't tell you the story. You can read the paper if you're interested. And we also came up with that kind of parameters. So that's not the best we can do. Currently, we are working on other type of figures that could be output from the package. So we have a package, and we are working on the outputs because it's not very satisfactory in that figure. So this was an undirected setup. This is the matrix of parameters QL, the connection parameters Q and L. So since it's undirected, you just see a triangular part of the matrix. So here it's the interaction between group Q and Q, and we tried to show the different values. So the 4 different columns are the 4 different time points, and the three different horizontal colors like that are the 3 different bins that we use. And we try to summarize the parameters in that figure, but okay, maybe I won't spend too much time on that because in a few months it will be different. Okay, so that's the end of it. Just a few conclusions. With this dynamic stochastic block model, what we wanted to do is to reconstruct the evolution of the groups through time. And the most important thing for us was to control the label switching issue between the different time steps, because we really want to have a model where we can follow the evolution of each individual. We want to track the individuals across the different time steps. Our model works with binary weighted data sets, and we have a model selection that we can perform through ICL. I have to admit that on many real data sets that doesn't work pretty well. That works very well on simulations, but on real data sets very often you don't have great results. So maybe you need to rely on other information to select the number of groups. And that's why I don't believe that we can select a number of groups per time point. That would be too much. So you can try the package. It's available. It's not on the cron. I left that and soon on the cron, but my co-author doesn't want to put it on the cron because it's too much work. I don't know. Okay, he's the boss on that part. I don't have my word to say. So it's available on this web page. And the paper is available on the internet also. Thank you for your attention.
Any questions? Yes. How I gather you're dealing with the groups as you define them are disjoint. So you're either at a particular time you're in one group or another. But it seems if you treat them as latent variables, at some point you're probably going to get a value between 0 and 1, say.
Yeah.
Or 0 and whatever. So how hard would it be to incorporate, not so much a distinct assignment, but a probabilistic assignment? I don't know if that would help in comparison to the results.
So there are many answers. First, it appears that with the stochastic block model, at the end of the algorithm, of the VEM algorithm, the posterior probabilities are very 1, 0. And we understand that there are some theoretical results. So I've wrote a paper with Mahendra Mariadasu where we've tried to figure out what's the behavior of the posterior distribution of the latent random variable conditional on the observations, and we understand why it does that. It's because that really goes to some Dirac distribution mostly distributed at the true value, a product of direct distribution. So that explains why VEM algorithm makes sense, because in an asymptotic setting, in fact, the nodes become independent, conditional on latent.
That's if the data is truly generated from the stochastic block.
Yeah, sure.
Real data.
So on real data sets, you observe at the end of the algorithm that you have 0 and 1 posterior probabilities. That's a feature of the stochastic block model. And the other answer is that there are overlapping stochastic block models that exist. This is useful. We didn't do that here.
Would it be harder, or would it be a lot harder?
It's always a little bit more intricate, but not that much harder. Yeah, could do.
What is ICL? How do you choose your penalty? Because I kind
Oh, it's just a big like penalty, BIC.
BIC.
Yeah.
Oh.
So the only thing is that this is integrated. Yeah. So this is integrated classification likelihood. The difference with BIC is that here you don't have the log likelihood. You have the something which is you plug in the z's. But here the form of the penalty is just BIC-like. I count the number of parameters, 1/2, and the number of observations. And the difference here between those two terms is that for the z's, the number of the observations are different than the number of observations for the y's.
Okay, I just missed this IC and was
I
kind of
didn't
a
say
little intrigued
Sorry.
what it stands for.
Any more? Yes.
Did you explore other type of approximations like the model field or simulated field to see how that?
No, we didn't. I'm not sure. Even in the static block model, I don't know if this has been done.
I thought that you were going to show us the example from ecology.
Oh yeah, so that's the paper we are currently writing. I'm sorry. So this was the stat paper, and now we are working on more examples from ecology. But in the beginning, I said I'm interested in animal social network. But for me, humans are animals.
Okay, perhaps we can thank Catherine again.
Thank you.
Very nice.